In this video, we're going to go over the first lesson in the Exponents and Logs booklet. So this lesson is going to deal with exponential functions. So when we talk about exponential growth or exponential decay, it occurs when an amount is either increasing or decreasing by a consistent rate over a period of time. Now the difference is that with exponential growth and decay, we aren't starting with an amount and adding some amount every time. So for example, if you had 1, 4, 7, 10, 13, right, where you're adding 3 every time, this is not an example of exponential growth. But if you have something like 1, 2, 4, 8, 16, etc., where something is doubling every time, this would be an example of exponential growth. So whereas this is a linear function where we're just increasing by some set amount, in an exponential growth or decay, because we could also be, instead of doubling, we could be going backwards and taking half every time, we're increasing or decreasing by some rate. So in exponential growth or decay, change happens more quickly than with this sort of situation of linear growth. So some common examples of exponential growth and decay are values and investments, population changes. Those are the most common ones we're going to look at. And we can generalize exponential equations as follows. So if you're looking for some value, you're going to start with the initial amount and multiply by the growth rate to the power of time. So let's look at a first example. Example 1 says Jessica is planning for her retirement. Her investment advisor suggests an investment that he expects to double in value every decade. So that's every 10 years. What is the value of $1 invested for 10 years? Well, that's quite simple. If she invests $1 and it's going to double in 10 years, she would have $2. Now, the next one asks, how long will it take for $1 to be worth $8? So here, we're looking to figure out when she would have $8. She's starting, the initial amount is $1, and the growth rate is 2. And we're looking to solve for how much time. So here, the time was 1 because we were working in decades, and this was 1 decade. Here, we know that 2 to the power of 3 is equal to 8, so that's 3 decades or 30 years. Now, you could use a table of values to determine how long it would take for $1 to be worth $26. So you can see here, after the time of 1 or 1 decade, the value would be $2. After 2 decades, it would be 4. After 3 decades, it would be 8. 4 decades, it'd be 16. After 5 decades, it'd be 32. So somewhere between 4 and 5 decades, or 40 to 50 years, that investment would be worth $26. Now, if we compare an exponential equation that expresses the value of the dollar in decades compared to it in X number of years, so everything we've been doing so far, we've had the value is equal to the initial amount times the growth rate to the power of time. And our time so far has been defined as the number of decades. If instead we wanted to know the number of years, we would have to take that number of decades and divide it by 10. So here, the value would be equal to the initial amount times 2 to the power of the number of years divided by 10. So in this above example, where we had 30 years, if we put that in here, we would have 30 divided by 10, or 2 to the power of 3. So you have to be really careful about how the variable is defined. So here, t was decades, or we could solve for years. On the next page, the next example is talking about a filter that removes 75% of the impurities of water that's passed through it. multiple filters can be used together to increase the purity of the water. So we can filter it through one filter and then another and another to increase the amount of impurities. So this situation is represented by A equals 0.25 to the power of n, where A is the proportion of impurities remaining, so 25% is how many impurities are remaining, and n is the number of filters used. So after using one filter, there would be 0.25 or 25% of the impurities left. After two filters, you could do to the power of 2, etc., etc. So explain why the base of the exponential function is 0.25. Well, that's because the filter removes 75%, but 25% is the amount of impurity that's left after the filter is used. So for example, you could be asked what proportion of impurities remains when 4 filters are used, and you would do 0.25 to the power of 4. So less than 1% would be left. And then in example 3, we have an investment type question. $1 is invested at 3% interest compounded annually. Write an exponential function to represent the value of the investment after t years. So here, the value of the investment is equal to the initial amount of money that's invested. So the value is equal to the amount of money invested times 1.03 to the power of time. Now the reason we use 1.03 is because the growth is 3%. So if you think about it, we're going to earn 3% interest, but then that amount will be added to the initial amount of money that you have. So when we're working in questions that involve compound interest, and we will see more examples as we go throughout this unit, we use 1.03 to show that we have the initial amount and we're adding 3% to it. So this would be the exponential function that we would use to represent this scenario. Now, in this lesson or in this unit, one of the things that we need to be able to do is graph exponential functions. So the graph of an exponential function has the form y equals c to the power of x, where c is a constant and it will always be greater than 0. So when c is greater than 1, the exponential function is increasing. If c is between 0 and 1, so I'll just make a note that this would be a fraction or a decimal, then that means that the function is decreasing. So on this table here, you can see the graph of y equals 2 to the power of x. So where the c value, the constant value, is 2, you can see that this function is going up and it will increase. Whereas when it's 1/2, it will decrease. And those should have arrows on the end. So this is exponential growth, whereas this is exponential decay. Essentially, this function, y equals 2x, means that our x values are doubling. Our y values are doubling as x increases. So here we start with a y value of 1 if we started just with our x is 0. 1, 2, 4, 8, 16, 32. So those y values are going to double as our x value increases. And for half, our y values are actually halving. So if I start up here, I've got 4, then 2, then 1, and then it actually goes down to a half, a quarter, an eighth, and continues that way. We'll look more at the graphs more specifically in a second. So the key thing to know about these exponential functions is that all exponential function graphs will pass through the point 0, 1. So they will all go through this point. The reason is that you have y equals some number to the power of x. Well, when x equals 0, it doesn't matter what that base number is. Any number to the power of 0 will be equal to 1. So all of these graphs, it doesn't matter if this c value is 2, 10, 50, doesn't matter. to the power of 0 will always give you a y value of 1. These graphs will also have no x-intercept because there is no value of x that will give us a y value of 0. Remember, there's no exponent that we could put in there that causes an exponential to be equal to 0. The domain will always be negative infinity to infinity. The range will be 0 to infinity. Notice that this is a round bracket, so here we have, XER for domain. And here this is y is greater than 0, but not equal to, because there's a horizontal asymptote at y equals 0. And again, that's because there is no value of x that we could plug in there that gives us a y value of 0. So if we look at the next page, you'll see that I've graphed here y equals 4 to the power of x and y equals 1/4 to the power of x, just so that you can see what these look like. So if we plug in some values of x, now the good thing with these graphs is that once you sort of know the basic shape, you will not need to draw out a table of values every time because these follow a very distinct pattern. So here, if y equals 4 to the power of x, I'm going to start with positive. I'm going to start with 0, 1, and 2. When you put in 0, then y equals 1. When you put in x is 1, y would be 4. When you put in x is 2, y would be 16. We're just doing 4 to the power of 0, 4 to the power of 1, 4 to the power of 2. Now remember when you put in a negative exponent, so -1, 4 to the power of -1, remember that becomes a reciprocal, so it's equal to 1/4. Same for 4 to the power of -2, that becomes this, or 1/16. So when we have these negative powers, we get fractional values. So if you look over at the graph, you can see here I've plotted the point 0, 1. I've plotted the point 1, 4. 216 is off of the graph. And I've also plotted the point 1/4 as best I can. And you'll notice here there's an asymptote at y equals 0. And this function is going to follow the asymptote here and then increase exponentially. When we look at a base of 1/4 to the power of x, again, here, when x is 0 or 1 or 2, we're just plugging in. So 1/4 to the power of 0 is just 1. 1/4 to the power of 1 is 1/4. 1/4 to the power of 2 is 1/16. With these ones, when you put in a negative exponent, again, we take the reciprocal and we actually get a positive value. And 1/4 to the power of -2 is 16. So our decreasing function, or y equals 1/4 to the power of x, starts up here and works its way down. So when x is -1, y is 4. When x is 0, y is 1. And when x is 1, it's 1/4. So you can see these are reflections of each other. Their shape is the same, they just go in different directions. One's increasing and one's decreasing. And finally, in example 2, we're writing a function for this graph. So the important thing to note is that 0, 1 will always be a point on an exponential graph. And if you go to the x value of 1, this will tell you what your base is. So this graph has an x value of 1 and a y value of 5. That means that y equals 5 to the power of x is the function that goes with this graph. That wraps up lesson 1. In the next lesson, we're going to talk about doing transformations on these graphs.